discuss section 4.6, this Euclidean domains. We know that division algorithm is possible in Z. I state the division algorithm for a positive integer n and any integer m belongs to Z. We have q and r belongs to Z such that m can be written as q times n plus r, where this r is equal to 0 less than or equal to r less than n, and this r is what we called remainder. This is the division algorithm. So here we have another evaluation, you say Euclidean evaluation, that is same as or that can be considered as a generalization of this Euclidean algorithm. So that is the first definition of section 4.6. Let D be a domain. A Euclidean function for D is a function phi equal to phi from D minus 0 to n, such that if a comma b belongs to D minus 0, a and b are non-zero elements of D, and a divides b, then phi of a less than or equal to phi of b. This is the first requirement of Euclidean function. And secondly, we have if a comma b belongs to D minus 0, then likewise there exists q and r belongs to D such that a is equal to bq plus r, where either r equal to 0 or phi of r is less than phi of b, strictly less than phi of b. If you consider this Euclidean algorithm in Z, we can get this phi of n equal to mod n is an Euclidean function on Z. Similarly, if you consider a ring of polynomials k of t, then phi of p can be, or Euclidean function can be defined as degree of the polynomial. So immediately when you define this Euclidean function, you can get this Z and this k of t are Euclidean domains. Whenever a domain possesses this Euclidean function that we called Euclidean domain, then this Z and k of t are Euclidean domains. Now we prove theorem 4.14. Every Euclidean domain is principal ideal domain. Principal ideal domain means an integral domain in which every ideal is generated by a single element. So let D be a Euclidean domain, I be an ideal of D. We will prove that this I is a principal ideal. That means every ideal of D is a principal ideal. If I equal to 0, it is principal because it is generated by 0 itself. Now if I not equal to 0, we will prove that if we are not considering the trivial case, that is always principal ideal. So if you consider non-zero ideal, then that I contains at least one non-zero element x. Choose phi of x. So if x belongs to I, that means I is not equal to singleton set 0, then you can evaluate phi of x for all x belongs to I. Okay, this is a function from D minus 0 or D to this n or Z, positive integers. Then you can say that it has a least element. So phi of x can be, we can make phi of x as small as possible. Then choose such element. If y belongs to the I, then by 2 we have y is equal to qx plus r. That means x is the least element in such a way that phi of x is small. Then for any arbitrary element y equal to y belongs to I, that can be written as q plus r, qx plus r, such that this r equal to 0 or phi of r less than phi of x. Okay, but we know that from this part of r is 0, we are done. R is 0, we can say that this y belongs to ideal generated by x. then we can say that I is any element of I is a multiple of x, then I is generated by x. Otherwise, what happens? Otherwise, our intention is to prove this r equal to 0. Okay, so then we consider phi of r not equal to 0, then we will get a contradiction. Then we can say that phi of r less than phi of x. Then what happens here? R, what is r? R is y minus qx. But this y is an element of I. Similarly, this qx is a multiple of x, then it is an element of I. Okay, so we can say that this is an element of I, and this phi of r is less than phi of x. So this contradicts the fact that the x is the smallest such that phi of x is small. So this is the contradiction for the selection of or the choice of this x. So we can say that this r never be non-zero. So r equal to 0. R equal to 0 means y belongs to this ideal generated by x, or y is a multiple of x. Then any element y belongs to I can be written as a multiple of x. Then I equal to ideal generated by x. Then it is principal. That means every ideal is a principal ideal domain. Now we have every principal ideal domain is a unique factorization domain. For that, we consider the statement every principal ideal domain is a unique factorization domain. Let D be the principal ideal domain. Since this implies D is Noetherian, that means D is a principal ideal domain, so every ideal is principal ideal. So every ideal is generated by a single element. So every ideal is finitely generated. Therefore, it is a Noetherian type. Okay. If it is Noetherian, then we can get factorization into irreducible is possible, that we have discussed in theorem 4.6. To prove the uniqueness, we will show that every irreducible is a prime. We just proved that a theorem before the 4.14, we have proved that factorization is unique if and only if every irreducible is a prime. Right? So we start with a irreducible P. Okay. We know that if P is the irreducible, then the ideal generated by P is maximal among the principal ideals. Maximal among principal ideals. But we know that D contains only principal ideals. So P is the maximal ideal of D itself. Okay. So we will prove that this P is prime element. In order to prove P is prime, we consider P divides AB, and we will prove that either P divides A or P divides B. If P does not divide A, what happens? Then we consider ideal generated by P and A. We know that this obviously this contains ideal generated by P. Since this A is not a multiple of P, that means P does not divide A, we can say that this ideal never be equal to this ideal generated by P. But P is maximal. Okay, so this is the only possibility of this ideal is D itself. Now we have P is P comma A is equal to I itself. Okay, sorry, this is D itself. Then shows that 1 is an element of D, implies 1 can be written as Cp plus Da. Okay, that is the statement. Now we have B is equal to Cpb plus Dab by multiplying B on both sides. But our assumption is P divides AB, so P divides this term and P divides this. Okay, so this implies P divides the right side, consequently P divides B. So whenever P does not divide A, we can get P divides B. This shows that every irreducible is a prime. That means the factorization into reducible is unique. Okay, therefore every principal ideal is unique factorization. Every principal domain is unique factorization domain. That means every Euclidean domain is principal ideal domain. That is 4.14. Here we have principal ideal domain is every principal ideal domain is unique factorization domain. Okay, consequently we have every Euclidean domain is unique factorization domain. This is section 4.6.